Today's lecture is on deployment and maintenance. It actually picks up with a few leftover pieces on testing, then moves into describing the deployment process and outlines some of the things that you should expect as you maintain large software systems. So definitions are, again, something that's kind of unavoidable in this class, and usually we don't have time in an in-class environment to get to this last little piece on testing, but it is sort of definitions all over again, just having to memorize these sorts of things. Most non-technical people think that fault, error, and failure refer to the same thing, but engineers have particular meaning for each of these terms, and the reasons, not that we want to have pedantic terms that we can argue over or arguments about these sorts of things, but that there are actually separate concepts behind these that we need to be able to differentiate. So a fault is just a static problem, a defect in the software, a problem with the coding, whatever form that may take. An error is an actually incorrect state of the program, a manifestation of the fault. So the fault has been executed in some way, and now there is actually a problem in the internal state of the software. And a failure is an externally visible incorrect behavior resulting from a software error. So you can kind of think of these as progressively more insidious or problematic. The fault is just an underlying defect. The error is a defect that has actually resulted in running problems in the state, but you may not be able to see those on the outside. And then finally, a failure is once you can start seeing this stuff from the outside of the software system. This leads us to the fault and failure model. Sometimes this is referred to as the PI model because if you read the steps backwards, P-I-E, you end up with pi. And these are all the conditions that are necessary for a fault, that static defect, to actually be executed, turning itself into an error, and then observed as a failure, right? So first you have to have the execution piece, right? There has to be a reachable location somewhere in the code. Then you have to have an infection step where the program is actually incorrect. The execution has resulted in some kind of incorrect state. And then finally you have to have a propagation where the infected state is now visible somehow in the output or interaction with the program. So this is the PI model of software testing, recognizing that at each of these steps you have an opportunity to catch the problem. And this differentiates testing and debugging as well. In testing, you're trying to find the inputs that will cause software to fail, and once you have a failure, the process of figuring out the fault, the location in the actual software that is incorrect, that is the debugging process. So when do you find faults? Right? When would you find a fault in a software system? This is a question that normally I would ask during the class and ask people to pause and think for a moment and then come up with a good answer. I'll give you a second here to do the same. So a fault is the static problem in the source code, and you really can only find a fault once you have a failure, right? So testing, if you think of the process as an opportunity to verify that the source code is doing what it's supposed to be doing, acceptance test type stuff, that is actually also your best chance to figure out all of the ways the process can go wrong and to find all of the faults in your system. So you can only find a fault given a failure once you have stuff that can be executed. And this is one of the big motivations for agile software development, is that the faster you get to some running code, some part of the thing that would actually be demonstrating what the user is expecting to see at the end of the day, the faster you can start finding the actual faults in that code, because you have to have a failure first. If you just have a whole bunch of source code that's theoretically interacting with itself and not producing anything that an external stakeholder or an external user would see, you really can't find all the faults. It's very difficult to find any faults in that sort of a scenario. All right, so let's talk again about more testing definitions. In this case, data, oracles, and cases. Test data is just the inputs or the values you'd have to provide the program to make sure that it's satisfying a single requirement or to execute a single method or a single function of the software. The oracle is what you are expecting to see when you provide that input, right? So you start executing the test. The oracle is the expected, intended behavior. Okay, and a test case is just a complemented pair of the inputs, the test data, and the expected outputs, the oracle. Okay, this leads us to observability and controllability. Observability is another definition that's kind of unique to testing. Essentially, we want to know how easy is it to see the program behavior based on its actual outputs and effects on the environment. This kind of goes all the way back to something we talked about very early on in the class when we were covering requirements engineering with Michael Jackson and the difference between the system and the machine. An observable program is one that has had some kind of visual impact on the environment, measurable impact on the environment. So if you have software that's really only affecting some kind of a hardware device, the back end of the system, or some other subsystem in the larger software stack, those are things that have low observability. It's very difficult to see the output and the effect on the environment. Software controllability is a little bit different. This is a measure of how easy it is to provide the program with the inputs that are necessary to produce certain behaviors. So if you have a program where there's lots and lots of inputs that are necessary before you're able to actually observe an output that you care about, that's said to have low controllability. Right? Easy to control software is something where you have a direct input from the keyboard or the mouse and an immediate response from the software system. Right? But inputs that are probabilistic or randomized or dependent upon some complicated internal state, like programs that rely heavily on parallelism or concurrency, they're said to have low controllability because it's very hard to get the program into the state that you expect a certain sort of behavior to happen. So both of these are problematic from a testing standpoint. Even if you can construct a good test case, meaning a good set of inputs and a good set of oracles, it may not be possible to execute because it may be very difficult to observe the expected behavior or to actually provide all of the inputs in the right order to the program. So again, normally we would have an exercise in this class, and I would walk through and see what you have come up with, and we discuss some of these examples. It's very important that you try and do these sorts of things on your own to try and come up with examples, especially examples where you can identify each of the definitions that we were talking about, right? So an example where you have the test data that you're expecting to provide to the program, the oracle, meaning the expected behavior you're expecting to see, and then think about the observability, the controllability, whether or not you would be able to see the failure itself, what would the error portion of this problem look like, and then finally, what kinds of faults might cause all of this to happen in the first place. So this is not the kind of thing that I would skip, even though it is an online lecture. It's very important to try and come up with these and make sure that you can identify all of the definitional elements that we've been talking about so far.